Okay, problem number 16. In this problem, we are asked to use integration by parts to calculate the integral from 1 to 2 natural logarithm of x divided by x squared dx. I want to spend a little bit of time to exploring different ways of calculating this integral. Of course, here we're given the suggestion to integrate this by parts, but what if you were not given that suggestion and you were just asked to calculate this integral? Now, you may have thought about calculating this integral by making a substitution. For example, one way to perhaps think about this integral is that, remember, the derivative of natural log of x equals to 1 over x. And we do have something in our integral. We have a part of our integral that is 1 over x, right? Because if I rewrite my integral as natural log of x times 1 over x squared, of course I can rewrite that as 1 over x times 1 over x dx. And so the fact that we have a term in our integral, namely natural log of x, whose derivative is another term in our integral, makes it perhaps a worthwhile idea to explore, namely to substitute instead of ln of x a new variable u. So what would happen if we were to try to substitute u equals to ln of x? So then, of course, the differential of u would be the differential of logarithm of x. Let's recall that the differential of a function equals to the derivative of that function multiplied by dx. So we would get 1 over x times dx. And that is actually a term in our integral. So right here we have 1 over x dx. I can replace that term with du. And of course, the first term in our integral, natural log of x, that could become u. However, we still have another copy of 1 over x hanging in the integral. And so if we were to make this substitution, we would need to express that remaining term 1 over x in terms of u. To do that, we would have to essentially express x in terms of u. And how would we do that? Well, we would go back to our relationship between u and x, namely u equals to natural log of x, and we would solve this relationship for x. We would then get that x equals e to the power u. And we would then need to go back to our integral and replace that with this expression. I would have to replace x with e to the power u. In other words, making this substitution would give us the integral of u times 1 over e to the power u du. And we would have to integrate from, well, let's see. So if x is equal to 1, then u is going to be natural log of 1, that is 0. Calculated here. U at x equals to 1 equals natural log of 1, and that is 0. So our new limit of integration will be 0. And when x is 2, u will be natural log of 2. Okay. And so note that I can rewrite 1 over e to the power u as e to the power negative u. let's look at what we have accomplished here. I was able to rewrite the integral that we had at the beginning in terms of our new variable u, and it does look a little bit simpler. We don't have a denominator. Well, if you write it as u over e to the power u, then we do have a denominator of e to the power u. In some sense, the integral became simpler. And actually, now that I look at this, we can finish calculating this integral by using integration by parts from here. So altogether, this idea of making this substitution was not really a bad idea. Let's see if we can finish this integration using integration by parts. So let's look here at this term in our integral, e to the power negative u du. I can write that term as the differential of e to the power negative u. That's not quite right. Let me put actually another negative sign in here. So then it would be correct. This is because differential of negative e to the power negative u would be the derivative of this function. And if you calculate the derivative of this function, you're going to get negative e to the power negative u times negative 1. This last negative 1 comes is included because of the chain rule. That's the derivative of negative u with respect to u. And of course, to get the differential, I need to multiply this by du. The two negative signs cancel out, and I get that e to the power negative u du equals to the differential of negative e to the power negative u. And right now, the integral looks exactly how we would want an integral to look in order to apply integration by parts, because it's written in the form integral of u dv. U is u and v is negative e to the power negative u. We're integrating from 0 to ln of 2. Okay, so now I can apply integration by parts. So integration by parts will tell us that, it's a continuation here. This integral will equal to u times v. Let's remember that v is negative e to the power negative u. And we're plugging in the limits of integration, which are 0 and ln of 2. And then we have to subtract from this integral of v, which is negative e to the power negative u, integral of du, and the limits of integration are also 0 and ln of 2. Okay, now for the first term right here, when we do the evaluation, if we plug in the 0 instead of u, the whole term becomes 0 because 0 times anything is 0. When we plug in instead of u natural log of 2, what do we get? We get natural log of 2 multiplied by negative e to the power negative natural log of 2. And then note that the negative signs right here, this negative sign and the negative sign inside the integral, they cancel out. So we actually get a plus integral of e to the power negative u du from 0 to ln of 2. And we can easily calculate the antiderivative for e to the power negative u. it will not be e to the power negative u, but it will be negative e to the power negative u. This is actually essentially what I've done right here. Remember, I wrote e to the power negative u right here, this term, as the differential of negative e to the power negative u. So basically I found the entire derivative of e to the power negative u. It's negative e to the power negative u. So I can actually just use that result here. Fortunately, ran out of space here a little bit. So let me go to the next slide and copy this expression. Okay, so our first term was natural log of 2 multiplied by negative e to the power negative ln of 2. And then we were adding to that integral from 0 to logarithm of 2 e to the negative u du. We can simplify here the first term. Note that e to the power logarithm of 2 is just 2. This is the definition of natural log of 2. Natural logarithm of 2 is the exponent of the power of e, which is equal to 2. And therefore, e to the power negative ln of 2, I can think of this as e to the power ln of 2 raised to the power negative 1. Remember, when you raise a power into another power, the two exponents get multiplied, and so we get 2 to the power negative 1, which is 1/2. And so altogether, for that first number in our result, we get negative 1/2 of natural log of 2. And then we get the antiderivative e to the power negative u. We determine that it is negative e to the power negative u. And we need to substitute 0 and natural log of 2 here. All right. So let's do this calculation. I'm going to skip down to here. So I have negative 1/2 ln of 2. Now when I substitute natural log of 2 for u into this term right here, I'm going to get negative e to the power negative logarithm of 2, and then minus negative e to the power negative 0. And we just need to interpret each of these terms. Negative 1/2 ln of 2. Then I have negative e to the power negative ln of 2. This is negative 1/2 as we just calculated. And then I have the two negatives here and here cancel out. And so we get plus e to the power 0, negative 0 and positive 0 is the same thing, and e to the power 0 is 1, so we end up with 1. And now finally, combining negative 1/2 and positive 1 gives us positive 1/2, and then we have negative 1/2 ln of 2. Making common denominator here, we get 1 minus ln of 2 over 2, and that is our final answer for this problem. Now, this is perhaps not the solution that the problem was suggesting at the beginning, right? Because the problem suggested to use integration by parts right away. It did not suggest making a substitution. So let me show you a different solution where we do not make any substitution. We just approach the problem as suggested by integration by parts. Also, I want to say that it is very often the case that integrals can be computed in very different ways. And so here's a second way to integrate this integral. Okay, so again, we start with integral from 1 to 2 natural log of x over x squared dx. And I probably should have written the integration by parts formula earlier. Integration by parts formula for the definite integrals looks like this. Integral from a to b, u dv, where u and v are some functions, equals u times v, this product evaluated at the endpoints of the interval of integration and the difference of the values taken, minus integral v du. So note how v and u switch places compared to how they are appearing on the left hand side. And we integrate from a to b v du. And for those integrals that can be integrated by parts, the most difficult part is deciding what part of your integral to select as u and what part of your integral to select as dv. Now, the integration by parts formula works when the differential of u, it looks simpler than the u itself. Maybe not just by itself, but maybe when it's combined with v multiplied by v. So the simplification comes from differentiating u, and if that derivative somehow, when combined with v, simplifies the integral, then we can use integration by parts. And the selection of what is u and what is dv is motivated by that. So you kind of have to look one step ahead. What is coming next when you use integration by parts and when you're making your choices. Now, one part of our integral is the logarithm of x, right? And the derivative of logarithm of x is 1 over x. Now, 1 over x is a simpler function than the logarithmic function. And so that actually tells us that maybe selecting u equal to ln of x is not a bad idea. So let me rewrite my integral. I'm just going to separate the two parts. The first part is going to be ln of x, and the second part is going to be 1 over x squared dx. And so what I'm suggesting here to try for us is to say that ln of x is going to be u, and then 1 over x squared times dx, that's going to be the differential of v. Okay. Now, before we can proceed, we need to figure out what v is. Now, finding v requires actually an integration, because we have dv equals to 1 over x squared dx. By definition, what is the differential of v? Differential of v is the derivative of v multiplied by dx. So, and by saying that dv, the differential of v, equals 1 over x squared dx, we are saying that v prime of x dx matches 1 over x squared dx. In other words, v prime of x, the derivative of v, must equal 1 over x squared. And that means that v is the antiderivative, at least one of the antiderivatives of 1 over x squared. And so to find v, we actually need to integrate 1 over x squared dx. Now, fortunately, this is not a complicated integral. We can rewrite 1 over x squared as x to the power negative 2. And then we can finish the integration by using the power rule. The power rule says that when you integrate a power of x, we need to increase the exponent by 1. So currently the exponent of the function that we're integrating is negative 2. We're going to increase that by 1. So x to the power negative 2 plus 1. And then we would need to divide by that new exponent. And then we would need to add a constant of an integration. Now, x to the power negative 2 plus 1, that's x to the power negative 1 divided by negative 1 plus c. And of course, x to the power negative 1 is 1 over x. Dividing that by negative 1 is the same as multiplying by 1 over by negative 1. And so this gives us the following information for what v is. V can be any function of the form negative 1 over x plus c. Now we don't need to, in this particular case, to apply integration by parts, we don't need to find all possibilities for what v could be. We just need to take one of these possibilities, and the simplest one is to assume that c equals 0 and v equals negative 1 over x. We don't need to complicate things for us with adding some constant. If we did, it wouldn't change our final answer in any way, and it's a good exercise to see why that would be the case. Okay, so now I go ahead, once we've determined what v is, I'm going to rewrite the original integral as the integral of ln of x, which is our u, times the differential of v, and we found that v is negative 1 over x. So this is the form we want to write our integral, original integral, in order to apply integration by parts, integral of u dv. And so now it matches this form. U is ln of x, v is negative 1 over x, and our integral is of the form integral of u dv. Now let's go ahead and apply integration by parts. So I'm going to take u times v, so ln of x multiplied by negative 1 over x. We'll have to evaluate this at 1 and 2. And then we'll have to subtract integral of v, which is negative 1 over x, multiplied by du, and u is natural log of x, so we're going to get d of ln of x. The integral is again from 1 to 2. All right, and for the first term, right here, when we do our evaluation, if I plug in x equals to 1, this limit into logarithm of 1 is 0, so that would not contribute to our result. Only the upper limit of 2 will contribute, and what will it contribute? It will contribute natural log of 2 multiplied by negative 1/2. What do we get for the second integral? So plus. First of all, the two negative signs will cancel out, this negative sign right here and the negative sign in front of 1 over x inside the integral. These two negative signs will cancel out. And also remember that differential of natural log of x will be 1 over x dx. So we're going to get plus integral from 1 to 2, 1 over x times 1 over x dx. So negative natural log of 2 over 2 plus integral from 1 to 2, 1 over x squared dx. And again, this last integral of 1 over x squared can be easily calculated by the power rule, since you can write 1 over x squared as x to the power negative 2, and then do the integration. So I'll skip to the result. You should get the entire derivative to be negative 1 over x, and then you will have to substitute 1 and 2. And when you plug in 2, you're going to get negative 1/2. When you plug in 1, you're going to get negative 1, and so you would have to subtract from negative 1/2 negative 1, and the total result of that for this second term right here would be positive 1/2. I don't have a lot of space here, but maybe I can squeeze in the final result here. So I have negative ln of 2, and then plus negative 1/2 minus negative 1, and the final result is 1/2 minus ln of 2 over 2. And that's the exact same result as we obtained earlier. So two slightly different techniques. The first solution used a substitution first and then integration by parts. Second solution had did not use any substitution, just used integration by parts right away.